Hello, thank you for the opportunity to speak today at the RSS workshop on geometry and topology. Title of my talk is Goldilocks and the Robot Brains. So just like in the story of Goldilocks and the Three Bears, we want to try to find just the right brain, something that's not too big, not too small for our robot, given a task or set of tasks that we'd like it to accomplish in some space of environments. And by brain, I just mean simply a computation block that is performing some iterations and receives data and sends out data. So fitting with the theme of the workshop, I want to look at geometry and topology and even some set theory and try to think about what's the right level to model the world or describe it in the robot's brain. So level one we'll call strong geometry. There we can talk about Rn and define differentiable manifolds, algebraic geometry, all kinds of other things. At the next level, two, we have weak geometry. There we just have very simple relational information, like in a certain direction is another object to the left or the right, where we don't have real numbers that we can use. We don't have coordinates in the usual way. So there we have combinatorial or event-based kinds of information. Oriented matroids would be an example of something that fits under there as a kind of structure. Number three, we have topology, where you have topological manifolds and then familiar notions of homeomorphisms, homotopy, homology, and so forth. And then finally, at four, we have set theory, where you can just talk about basic sets, unions, intersections, mappings, subjects like category theory fit in there. Now, think about what makes two mathematical objects equivalent, or two spaces equivalent under some mappings. So this varies as we go down through the numbers here. So in strong geometry, we consider two spaces to be equivalent if there's an isometry between them, maybe an orientation preserving one. At level two, we want to have a mapping that preserves some kind of combinatorial structure that has to do with the relationships of how objects are distributed in the world. At level three, we have homeomorphism or homotopy equivalence or homological equivalence. At level four, just a simple bijection between two sets would correspond to some kind of equivalence. Now, one thing to note is that just because a mathematical object requires more definitions to set it up does not make it more general. So that's kind of contrary to a lot of engineering, and I think it's tempting to get confused by that. So so the more general levels here are the ones further down on my list. So set theory being the most general, of course. So just because you have to define more things doesn't make it more general. It's in fact usually less general. And with regard to probabilistic modeling, this could be applied to any of these levels, but I'm not going to do that today. We've done that with some of our works in some of the things that I'll talk about here. But I'm not going to cover that today because I think it kind of obscures some of the central message of this talk. So let's think about a robot and its environment. So the environment is a physical world. It can be unpredictable. It has a lot of challenges. We want to manipulate it in some kind of way. The robot has in its brain just a kind of computation block, as I said. Information comes in from sensing, so there are observations coming in all the time. And then the robot sends commands out through some kind of form of decision making, and these commands cause actuation in the physical world. I want to compare two spaces. There's a state space, X, which is external, and this corresponds to the configuration or phases of the robot or object properties, anything we want to describe about the actual external physical world. And then there's an internal information space that corresponds to what's in the robot's brain. This could be data structures, belief states, any kind of memory that the robot needs to make decisions. I view this as a coupled dynamical system between the external and the internal, and then a kind of dividing fence, if you like, between the two. So there's this mapping H, which is a sensor mapping, and it maps states to observations, then they become internal. And then there's a strategy or plan, which goes in the other direction. It maps internal states to actions, which affect the external world. So this becomes a kind of coupled dynamical system between the internal and external states in this way. And when I talk about information or information states here, I'm using the notion of information not in the Shannon information theoretic sense, but in the von Neumann-Morgenstern game theoretic sense. So in a sequential game, there's uncertainty about what the state is. And this seems very natural in the case of robotics, because the robot should be uncertain about what's going on in the physical world, and it can't measure everything, but nevertheless has to make a decision based on that. So that's why I think this notion of information is appropriate for robotics. So one goal then is to make these information spaces as small as possible. I talk about these as information mappings in my planning algorithms book from 2006. So the idea is we want to take these histories of observations and actions that are commanded and reduce that down to some smaller kind of structure. We may want to just do state estimation, and then you could apply a state feedback control law. We may just want to measure the time, and that's all. And then we have what's called open loop, just time feedback. We could just use the last sensor observation and have sensor feedback. Many different possibilities. We could have a Bayesian decision-making paradigm and then have probability density functions calculated based on the information. A special case of this, a very useful case of this, is the Kalman filter, where all the decisions are made based on means and covariances of these probability distributions. So the challenge is to find the right mathematical space. And what we want to do is compare two different spaces. So we have a state space, X, which will have the maximal amount of information that we want to consider. And we don't actually measure it directly, but we just define it mathematically, and it serves as a reference for analysis of what we would like the robot to do. So if we define some kind of model of how the robot operates, we want to then prove that it does the right thing back in this reference state space. The internal information space should be chosen according to this Goldilocks principle. So the idea is we want to figure out what information is actually necessary, what sort of internal representations or memory should the robot have, so that if we took something away, it wouldn't work anymore. It'd be impossible for it. And then we want to also, of course, have it be sufficient for solving the tasks. So we need to strike the right balance here and find this. And I think that these topics of the workshop fit perfectly: strong geometry, weak geometry, topology, and set theory. So I'll go through and look at each of these cases and highlight some previous works that we've done in that context. So let's first look at strong geometry. So look at the robot motion planning problem. So I was fascinated with this going back to the 1990s when I was in graduate school, also called the piano movers problem. Here we have perfect three-dimensional geometric models, and nowadays we can do this with SLAM. We have cameras available and IMUs and nice software libraries. We can build three-dimensional representations of the world and put all of that into the robot brain. Then we reason about the configuration space of the robot. So we do a search through the space of transformations of the robot. And in this space, it's very general. We try to get from an initial configuration to a goal configuration, and we avoid these obstacle regions where there may be collisions. So in terms of mathematical modeling, the motion planning problem generally can be described as semi-algebraic constraints on a topological manifold that's embedded in Rn. This n is typically higher than the number of degrees of freedom. There's other ways to encode it and such, but not too much higher than the degrees of freedom. We can also consider nonlinear robot control systems in general, with the usual formulation x dot equals f of xu and y equals h of x. And we use some local coordinates of a differentiable manifold in general. Embedded in Rm, which again, m is some higher, maybe more than the number of degrees of freedom, and including phase information that's encoded in the state space. So the kinds of tools that are applied to solve these problems: for earlier motion planning, the exact or complete methods, the tools were computational real algebraic geometry. There's a lot of computational geometry that's applied in sampling-based motion planning in the form of collision detection, maybe KD trees, other kinds of data structures. And methods like RRTs and PRM often rely on these. And then in terms of solving nonlinear control problems, differential geometry becomes the important methodology for constructing solutions, and then also numerical methods get applied quite frequently. But the trouble is that we want to think about the internal representation that the robot has. And in this case, do we really need to maintain complete geometric information? And when I think about this, I'm reminded of the notion of a Cartesian theater that Daniel Dennett introduced in his Thoughts About Philosophy of Mind. So in this case, people have believed in this kind of Cartesian duality for quite a long time, or at least there's some remnants of it that seem to exist, where in order for the brain to make decisions, it must be representing something that's quite complete in its picture of the physical world, as if there's a full theater playing out all the time. And so this is a very strong sort of representation-oriented philosophy, and it seems a bit absurd. And in order for that to happen, then it seems like the decision maker inside of the head would have to also have a complete Cartesian theater going on inside of it, and this would just keep applying recursively, so it leads to some kind of absurdities. So I feel like we're doing the same kind of things very often in robotics. It's tempting to just sense everything in the world around. Sensors are cheap, memory is cheap. Let's just put everything in the robot and then discard information as needed to make decisions. So why bring it all in and then discard it? Why not just sense what's needed, build only the representations that seem to be necessary for making the right decisions? So I think that's the right kind of thing to be doing for robotics. So going along in that direction, let's look at weak geometry. So suppose you have a robot that moves around in the plane. It's this white disk here. And then in the plane, we have a number of landmarks, each one with a unique number. And then the sensor that the robot has just simply reports the cyclic permutation of these landmarks, just sweeping around, say, counterclockwise. And as it moves around, it will observe different permutations of these. And that's all it gets, and it's also able to go towards a landmark. So one thing we showed is that if we move the robot around like this, without letting it have access to real valued coordinates at all, so it can't tell x and y positions at any point, we determined that it can learn a representation of its environment that contains a lot of geometric information. It can answer any question about convex hulls. For example, for a given triple of landmarks that forms a triangle, it can answer a question about whether any other landmark is inside or outside of that triangle. So this is equivalent to, in computational geometry, the dual line arrangement. Every point becomes a line, and then there's a kind of structure that has two-dimensional cells and one-dimensional cells and zero-dimensional cells. So it can learn this, and it contains a strong amount of geometric information, but it's still weaker than the full geometric picture. You can extend this a little bit. You can say that the robot also observes whether a landmark passes in front or behind the other as it moves around. This will actually then form information states that are braids. And then you can imagine braid groups and knot theory and topology coming into that. I'm not going to talk about that, but it's just a little teaser. There's all kinds of ways to introduce interesting mathematics here. We also came up with a version of this problem where the sensor just measures the depth ordering or distance ordering to the landmarks. So for example, if the robot's here, then it would observe the ordering 2, 1, 3, 4. That's the order of the landmarks from closest to furthest. Based on that, it turns out that the robot, by doing some simple motions, can learn the Delaunay triangulation and again answer convex hull kinds of questions. So it can do basic navigation in the environment by sensing these landmarks in this very minimalist way, but it never has access to XY coordinates. As another example, at the nonlinear control level, we looked at a collection of n vehicles in the plane that move around like Dubin's cars, and the goal is to get them to all rendezvous in some place. We can't specify what place that will be, but we just want them to rendezvous. And the way they work is by observing other vehicles in its windshield for each vehicle, and the windshield is very wide angled. It doesn't know the precise position of any one of the vehicles, but if a vehicle moves off the left or off the right, it's notified of that, and the robot can rotate to try to bring it back into the field of view again. So the robots or vehicles all move in this way, and they're just trying to find another vehicle to chase. And in doing this, we showed with some somewhat non-standard Lyapunov convergence proofs that we can get all the vehicles to converge, even though they never have access to coordinates of themselves or any other robot. So they can't do any kind of localization. They just keep flying by trying to maintain basic visibility. They don't even know the precise angle to where the vehicles are. Now let's go to the level of topology. So I want to define something I call a simple gap sensor. Imagine you start with a robot in the plane here, and it has a omnidirectional depth sensor. So think about that, and as it measures depth, there will be discontinuities in those depth measurements. So this corresponds to some sort of interesting topology at a very basic level. So if I were to just plot out this function, which I've done here, this depth function, then you notice there are several connected components. There are 5 here in the depth measurements, and then there are these discontinuities. So what if I have a sensor that just measures these gaps? It just senses that there are, say, 5 gaps, and it keeps track of these in a kind of combinatorial way. And as the robot moves around, it moves a little bit, it notes that that's the same gap. It's able to do these associations. So if it goes moving around like that, I want to figure out what the robot can do as there are these topological changes in the depth. Just these connected components change. Well, it turns out if the robot moves up and down here, in this example, then a gap will appear or disappear. And this corresponds again to a topological change in the depth information. If it moves up and down in this bottom case, then gaps will split or merge. So those are the 4 cases that we need to think about. And then we can place the robot in the environment, and we can build a kind of minimalist filter that keeps track of the splits and merges and appears and disappears that have occurred. And then when it's done, it's able to actually move back to any place where it's been before optimally. And by optimally, I mean in the shortest possible way in terms of Euclidean distance. So it actually learns the pieces of the reduced visibility graph or shortest path graph, which is really interesting, I think, that it's able to do that and then do distance optimal navigation without ever measuring distances. The only thing it's able to do is move towards gaps, and then the gaps will appear, disappear, split, or merge as it goes out and moves around. So it's using this topological information to navigate, but yet still does something impressive in terms of the original big state space. Another example of this is very closely related is what we call shadow information spaces. So in this case, you have a bunch of moving targets or bodies in the environment. So they're shown here with different colors. They're in different classes within which each one is indistinguishable. So there's a bunch of, say, green targets moving around, red targets, blue targets. And then there are these white bodies that move around carrying sensors. So these could be the robots out moving around. And what we want to know are upper and lower bounds on how many targets there are in each one of the connected components of the so-called shadow region, which are the places where none of the sensors are covering. So each one of these robots has this omnidirectional visibility views. They don't have to be omnidirectional in this approach. It can be any kind of coverage you want with sensors. And then we just keep track of topological changes in these shadow regions. So the way to do this is to just keep noting when different regions of shadows appear, disappear, split, or merge. It's the same events that we had back in the case where I talked about optimal navigation. So it's this splitting and merging and appearing and disappearing. The same events occur. And we can reduce this problem into a very efficient integer linear programming task that involves keep tracking upper and lower bounds for each one of these shadow components. And then there's some very simple rules to apply when splits, merges, appears, and disappears occur. And so then at this point, we can keep track of how many of these moving targets there are. When they're all inside the field of view, we can count those, but then we can also then figure out in these shadow regions how many there are in terms of upper and lower bounds. Another example we call obstacles and beams. Imagine there are sensor beams placed around in the environment. Here's just a planar example. The robot goes out moving around along this blue path, and then each one of these beams, which could be implemented by a simple emitter detector pair or could be a camera of some kind, doesn't really matter. As the robot goes moving around, a letter gets spit out every time one of these is crossed. So now this seems to suggest that there's some kind of nice algebra that's created as robots go out and move around through these different detection regions. And so in some of our previous work then, we've shown that you can calculate the regions that the robot has been to if these beams divide the workspace of the robot or environment of the robot into these regions. We can show we can recover what sequence of regions the robot has been through. Or we can reconstruct paths up to homotopy equivalence. So that's another example of what we can do with these kinds of things. And we also have many different variations and extensions. You can make directional beams, and you can consider any kind of relations you want to talk about equivalence of paths for the robot in connection with what kinds of sensor observations occurred. Now let's look at the level of set theory. So suppose in a very general setting, you just have a state space X, and then you have a sensor observation space or output space Y, a sensor mapping is H, and then the preimage of an observation is given by this. It's the set of all X's that could produce the same Y for a given Y. Think about that. That's the fundamental kind of uncertainty that we have in robotics, one of the most fundamental. We can't measure everything in the physical world with our sensor, but we get some observation. And even if the sensor is functioning perfectly, forget about noise and quantization and other sort of problems. But just in an idealized setting, we're not measuring everything. That's what this preimage is telling us, what we're not measuring. Now let capital pi of H be the partition that's induced by this sensor mapping H. So that's, in some sense, telling us how finely the environment is chopped up by this mapping. So for example, if the state space is a subset of SE2, you have a planar robot that moves around X, Y, and theta, so it can rotate as well. Then imagine a depth sensor, a directional depth sensor, that gives a single reading, like the robot's 1 meter from a wall in a, let's say, polygonal planar environment. So think about the set of possible configurations that correspond to that measurement. that's a two-dimensional subset of this configuration space for this robot. So pi of h, capital Pi of h, corresponds to slicing this configuration space mostly into some kind of two-dimensional sheets, with some special cases where there's lower dimensional components as well. That's how the configuration space is sliced up by the robot having a depth sensor in this environment. So now suppose we want to compare the power of sensors. We want to know when one sensor is better than another. And by being better, it should be able to simulate the other. You should be able to take the output of one sensor and generate the output of the other. So this happens if and only if the partition of, so let's say H1 is a refinement of H2, then H1 dominates H2. It's better than H2. That means we can take the output of H1 here, which is Y1, and there exists some function G that lets us transform that into the output of sensor 2. So that's the basic idea. Now, it may be computationally feasible or may not be computationally feasible, but if you don't have this domination relation satisfied, then it becomes impossible to reconstruct what the other sensor would have done from the first sensor's output. So if we take then more and more sensors and we think about the set of all possible sensors for a fixed state space, so all mappings x to y, and we also say that two sensors are equivalent if and only if they have the same partitions produced from them. So this gives us a way to kind of organize them all into nice equivalence classes. Then the set of all partitions of X forms a sensor lattice, or in some sense, the set of all sensor models forms a lattice of partitions. Looks something like this. This is a very simple example with only 4 states, but of course there's much more states in general. At the top of the lattice, you have all bijection sensors, which partition the state space into singletons. At the bottom, you have a kind of dummy sensor where you just have the original set X itself, and that's all that's in the partition. And then you have all kinds of possibilities in between. And then we can extend these notions to state trajectories that are time parameterized. So this is a mapping from a time interval into the state space. We could also represent it as a kind of Z space here by just taking the Cartesian product of X and T. And then we've defined partition lattices not only over the state space, but over the state time space and even the trajectory space. And we developed a very general notion of triangulation that goes back to ancient triangulation principles that were used for localization and amounts to traveling through this partition lattice over the trajectory space every time new data is received. So this corresponds to the resolution at which the world is being sensed, and the goal may be to get all the way to the top, which is being able to estimate the state or observe the state perfectly, but that's not what happens for most of the tasks, or not even what's needed for most of the tasks that we would like our robots to solve. We'd like to figure out how far up we need to go in this lattice to solve the problem and not accidentally drop down so far that we can't solve it anymore. So this helps express this kind of Goldilocks principle that we'd like to have. And going down the path of towards minimality and trying to reduce the information requirements as much as possible, it's very important to think about the kind of motion primitives that your robot can do. Sometimes you can get the robot to do a lot by having little or no sensing information. So let's look at this. This is what happens if you just take a robot and let it bounce off the walls like a hockey puck, and in this case moving around in a complicated simple polygon. So it turns out for almost all simple polygons and for almost all initial conditions, if you let the robot bounce around like this, the resulting path will be ergodic, which means that every open set will be hit, and it's also very strongly uniform in some sense. So this is quite a nice kind of result. And what does it take for the robot to accomplish this kind of very simple bouncing? Maybe it needs very little sensing just to ensure that it did a kind of perfect, let's say, billiard bounce. Maybe it's done in some mechanical way. So it needs almost no information to accomplish this kind of thing. We've done some implementations with robots like this and built and developed small information spaces that are used for feedback that can force robots to do things that we want as long as they have these motion primitives. So for example, here are a couple of differential drive robots that move in a planar environment where there's 3 different regions that are divided by some colored tape here, and the robots consider those to be barriers, or they can pass through them based on the information state. And what we want the robots to do in this example, the task was to get them to patrol in a clockwise manner, but never be in the same region together among these 3 different regions that we have that are each with 120 degrees of width. So that's the basic idea for that. So we can do this with very simple state information state feedback, which I don't have time to explain in detail here, but I just wanted to give you that. So some final thoughts. The general idea here is don't sense everything in the world, even though sensors are cheap, computation's getting cheaper, memory is cheap. Don't sense everything in the world and then perform some intense computation to get what you actually needed. Try to sense what's only needed and forget the irrelevant information as early as possible. This reminds me of forgetful functors in category theory. When I first heard the idea, I thought it was kind of strange. Now it makes more and more sense to me all the time. So forget what you don't need. Leave it in the physical world. Don't even sense it if you don't need it. So that makes to me that makes the most sense. Also, remember that some clever architectures may be employed to be properly forgetful. So you may be able to hide some of the information that would have been needed down in lower layers. And in trying to move towards this philosophy of minimalism, I'm reminded of Rodney Brooks's subsumption architecture and his philosophy that the world is its own best model. And I think back in his work in the 1980s, he was reacting to people trying to build very strong models that were much more like the Cartesian theater. That term wasn't used at the time yet, but this kind of tendency has been occurring sort of all the time. And he was reacting very strongly to that. But I think he went all the way to an extreme of having almost no kind of modeling or no representation in the robot. And I'm advocating for having just enough with this kind of Goldilocks principle so that the robot can accomplish its tasks. So we want to know what are the right minimal structures. The same would apply with regard to machine learning. Are the right minimalist structures even there in the space of possibilities that you're searching through or optimizing over for your machine learning applications? We want to be able to find the right geometric, topological, or set theoretic structures that are matched to the tasks that we want our robots to achieve. Let me finish with one nice little puzzle that illustrates a lot of the concepts here. We have a robot that doesn't know whether or not it's moving in the plane. So the robot has XY coordinates that it can sense, and it can move around in what it might think is a circle, but we don't tell the robot whether it's in environment A, which in fact is a circle, or it's in environment B, which is a helix. And we give it one task, which is find a treasure, which is a landmark in the environment. So the treasure's there, and if it touches the treasure, if it moves on top of it, then it detects it. So think about what happens after it moves around in one full revolution. So what happens is it immediately knows that the environment must be a helix. And then it can do some lost cow kind of searching, doing clockwise and counterclockwise motions back and forth until it eventually finds the treasure. But it's interesting that it was able to deduce what environment it was in right away. In the case of task number 2, I say determine whether or not there is a treasure. And in that case, after it moves around one full revolution, it can only say either I'm in a circle and there's no treasure, or I'm on a helix and there may or may not be a treasure. And it can never decide whether or not there is a treasure. So it's very interesting in that the topology of the environment and localization and SLAM all come together here. And the task as well that you'd like the robot to do gets affected by this. So for one kind of task, it doesn't really matter so much. It can accomplish it, but for the second task, it cannot accomplish it based on this topological difference. So it's one of the simplest examples I could think of where all of these issues are tangled together, where just not being able to distinguish between whether the environment looks topologically like S1, the circle, or like R, the real numbers, makes a critical difference into whether or not the task can be solved. Thank you very much. The next speakers are Vyacheslav Borovitsky from the Steklov Mathematical Institute in St. Petersburg and Alexander Terenin from Imperial College London.